There's another situation that can occur that looks very much like the other one, but I want to talk about this in comparison to the one we just did on the other slide. If I make a very small change to this differential equation, two changes actually. One is that I'm going to put a negative in front of the r, and the other is that I'm going to erase k and replace it with t. If I graph this differential equation now, I get critical values, or what will eventually be the locations of my equilibrium values of 0. Y equals 0 makes this whole thing 0. So let's go ahead and plot that. And the other one is where this expression here, this factor, is equal to 0. Well, this factor will be equal to 0 if this expression here is 1, because then I'll have 1 minus 1. And this will be 1 if y is equal to t. So I'll have another equilibrium value at y equals t. I should probably also label my axes here. This is a graph of the differential equation, dy dt, in terms of y. Well, this is going to be a parabola because I have a y squared term here. That's the highest power. But notice that when I multiply through this negative value here, negative r, that's going to turn this y squared value positive. So it's going to be an upward facing parabola with a vertex halfway between the two zeros. I should label this one too. This is t. This is 0. This is t over 2. And so I'm going to have a vertex at t over 2. Well, that's my y value. But this is an upward facing parabola. Since I already have my two roots there, then my vertex must be down here somewhere. And my parabola would look something like this, assuming I can draw relatively well there. When I plug t over 2 into my dy dt equation, I get negative r times 1 minus, I'm plugging t over 2 in for y, and I get t over 2 here. This just becomes t over 2t, which is 1 over 2, that's a half, times t over 2. Well, that's negative r times 1 minus a half, that's a half, times t over 2, which gives me negative r t over 4. So this point right here is t over 2 comma negative rt over 4. Those are the coordinates of my vertex. Okay, let's take a look at what this tells us about the graph of the solutions. And I can start with my zeros, where I have a 0 on the graph of the differential equation. I'm going to have equilibrium solutions in my solution. So I'll have, make my pen just a little bit bigger here. I'll have a solution, I'll have an equilibrium solution at y equals 0 and another one at y equals t. I will label those. Y equals t, y equals 0. And now I'm interested in what's going on down here, in between and above. Let's go ahead and do the in between part first. I'll go ahead and get my pen ready again. In between y equals 0 and y equals t is in between y equals 0 and y equals t. This is the graph of the slopes of the solutions. So my slopes here are all negative, so they're all going to be pointing down in between those two horizontal lines. They start small negative, get large negative, and then by the time they get over to t, they're small negative again. So in halfway in between 0 and t, which is right about here, my slopes are as large as they're going to get, but they're negative. And then either side of that, they're negative but not as steep, and still negative but even less steep. I'm doing this very quickly because we've done quite a few of these now, and I'm hoping that you are comfortable with the process here. There we go. To the right of y equals t is going to be above y equals t here. There my slopes are all positive. They start small and get steeper, get bigger. So I'm going to have positive slopes that get bigger as I go away from y equals t. Going really quickly here. It's less than ideal, but I don't want to take too much more time on this. It's already been a very long section. To the left of y equals 0, which is going to be the below y equals 0 over here, my slopes are again positive, starting small and getting bigger. So I have positive slopes here, but not very big positive slopes. And then larger positive slopes. And larger still. Okay, that's not the best job I've ever done, but it'll do. You can see my two equilibrium solutions. One is here, and the other is here. And other solutions are either going to start above the equilibrium solution and just go away from it, start well below it and come up to it. So we have kind of an asymptotic, not kind of, we have an asymptotic behavior there. We have an asymptotic behavior above as well. Or finally, they're going to start near y equals t and approach y equals 0. Okay, that's not the best graph I've ever drawn. Now here we can see that this equilibrium solution is stable because everything is moving towards that horizontal asymptote there. So we'll call this the stable equilibrium. And this one is unstable. Everything's moving away from that solution. So we have unstable. On the previous slide, we had something that looked a little more like this. We had, I have to keep changing pen sizes here. We had equilibrium solutions that looked like this, and then we had graph curves that looked something like this. And I said that that was in part, draw another one there, due to the nature of the population that was being traced here. Here what we've got is a very low, I'll start with this one, a very low number in the population, and they're put into an environment where there is sufficient food and other resources, and they grow, but eventually they're going to run out of food, or they're going to populate, reproduce enough that they don't have enough resources to share amongst themselves, and so their population levels off. And of course, in reality, what happens is that other factors are involved, and we lose population, but that's a separate factor. We're not looking at that situation at the moment. We're going to assume that the population has everything it needs to survive and thrive in the absence of other factors such as prey or I don't know, weather, bad weather, things that wipe out food supplies and so on. And so they're just going to continue to, the population will just continue to grow to a point, right? There is only so much space in a field that deer, for example, can occupy. So the population will level off. But what's going on up here is very different. Here we have a population starting very high. Actually, before I go back to that one, let me talk about this situation here. If we had in the previous slide, if we had a population that was too big for the environment, it would quite quickly drop off and reach this capacity, right? So whether you start with too many, or let me rephrase that, if you start with more than the environment can support, or fewer than the environment can support, it will reach the carrying capacity in either case eventually, right? So this is very different up here because we're starting with near capacity and going away from it. Here we're starting near capacity and dropping down to zero or close to zero. So what's going on here? Well, for some species, they won't the species won't survive if they don't reach some kind of critical mass, right? If there aren't enough individuals in the population. If there are enough individuals, a minimum of T, then the species can grow, at least theoretically, without bound, right? They can reproduce infinitely. If there aren't enough individuals in the population, then they simply die off. There has to be this sort of minimum number of individuals in order for the species to be able to continue to thrive. If there's a few too few or a whole bunch too few, they're just going to die off. It may take time, but that's what's going on with this curve here. In this context, we call this equilibrium value not a carrying capacity, but a threshold. So it's a slightly different terminology. We talk about threshold, we mean a minimum number necessary for survival. And if we talk about carrying capacity, we're talking about a maximum number of individuals that can exist in that environment without the resources in the environment running out. So far in this section, we've talked about logistic growth and something called threshold. In logistic growth, we have an equation that looks like this. Notice that I've moved the R from here over to this side. I think it's tidier. In this equation, K represents the equilibrium solution, one of the equilibrium solutions, but specifically it represents saturation level, or what we've been calling carrying capacity. In this equation, it looks exactly the same, except I've exchanged the K for a T and I've put a negative in front of the R, and the T represents something called threshold. The presence of this negative sign in front of the whole thing, this makes when I graph this, I get an upside down parabola. When I graph this, when I get a right side up parabola. And the ramifications of that are really quite interesting, right? We found that in this situation, if the environment was just right, then the population would grow to meet the capacity that was available for it to grow into. In this situation, though, if you didn't have enough individuals to start with, then they wouldn't, in fact, reach the carrying capacity or a carrying capacity. The population would instead reach the other equilibrium solution, which was 0. The other thing about this situation here, though, was that if you had too many individuals in the population, or if you at least had more than the threshold, the population could grow unbounded. And that's an interesting thought. But we have one more scenario that kind of modifies this situation and lets us take into account that that's an unlikely situation, unlikely to happen. We have dy dt equals ry times 1 minus y over t, which so far looks just like what we have above. But now I'm going to multiply that by a capacity factor. Looks like this. So basically, this one has, oh, I forgot my R. Let me stick that in here. Ry. So this equation is exactly the same as this equation here up to this point. And then I've tacked on the factor from the logistic growth equation. And what this is going to do is cap the potential growth at K, which would be somewhere above T. So let's take just a minute and graph this differential equation and see what it tells us about the various equilibrium points or equilibrium values and what the graph of the potential solutions looks like. You can see from this equation that we're going to have zeros of y, t, and k. Let me take just a moment. I'll grab the right pen and show you very quickly again where this comes from. This factor, this will work for the other one, equals 0. If this factor equals 0, then the whole thing will be 0. And how does that factor equal 0? It equals 0 if 1 equals y over k, multiply both sides by k, you get k equals y. So when y equals k, this factor is 0. So also when y equals t, this factor here will be 0. And those are the things that produce zeros on the graph for us. So I'll switch pens again. We have an equilibrium solution here. We have a 0 for this graph here, we have one, I'm going to call this and this my other solutions. We have this other stipulation, I haven't written it down or discussed it explicitly yet, that t is somewhere between 0 and k. In other words, t and k are both positive numbers, but k is bigger than t. And the other thing that we need to make sure we're aware of is that r is greater than 0. And these parameters are true of the other equations as well here. This r is always greater than 0, which means this is going to be an upside down parabola. If r is greater than 0, this is a negative number, which means the y squared term is positive, so it's going to be a right side up parabola. But this one here, if r is positive, then this is negative times a negative y times another negative y. So I'm going to have a cubic here, but rather than a cubic that looks like this, I'm going to have a cubic that looks like this. It starts high. It's kind of an upside down cubic. So that's an important piece. And I'm just going to use graphing technology to produce the graph of this function here. And again, I should do a better job of labeling my axes. This is y. This is dy dt or y prime. All right, I'm going to go graph this and come back. It takes me so long to graph something like this with any kind of, I don't want to call it accuracy because I don't know what t and k are here, but just to make it, look like a nice graph. So I went away and I made a pretty graph and then I came back. I also moved this point here. I can label these. We have k is the biggest. So k here, we have t here, and this of course is 0. I'm not going to worry too much just now about the vertices. They're not really vertices. I don't know what to call them. But the local max and min here, I'm not going to worry too much about those. We can find them if we know exactly what these values are, but without them, it's kind of difficult. We could find them generically, but we've done that for these other graphs as well, and I think that's enough for this. So this is the first time we've had a cubic for our differential equation graph, but I can use it in the same way. If I have a graph of t against y, I can tell from my differential equation graph where the zeros are going to be. They're going to be at y equals 0, y equals t, and y equals k. I moved t over, by the way, because it looked like it was halfway between 0 and k, and that's not necessarily the case. So I have an equilibrium solution at y equals 0, an equilibrium solution at y equals t, and another one at, see how I do this, y equals k. And I'll just label those. Y equals k. Y equals 0. There we go. In between 0 and t, my slopes are negative, small, negative, large, and then negative, small again. Between 0 and t, I have my largest, oops, get a different pen. My largest slopes are halfway between 0 and t. Then they're smaller and smaller still. And they're smaller and smaller still. But negative, they're all negative in here. Between t and k, they're small positive, then large positive, then small positive. So I have small positive, large positive. Not much room for change in here because it's a smaller range of values. And to the left of y equals 0, which means below y equals 0, I have positive and growing. So we have positive, oops, positive and growing and potentially unlimited. Well, it's getting really sloppy. And to the right of y equals k, above y equals k, I'm going to erase that axis label there because I need more room. I'm going to have small negative increasing to larger negative. So I have small negative increasing to large negative. All right, and so if I trace these out, I get something like this down here, something like this in here. This is really hard to see in here, but it's going to be small negative, larger negative, and then small negative again. Positive. And finally up here we get something that looks like this. So in this scenario, what we have is that if you start with a population near threshold, then you don't have enough individuals to sustain the population, so the population eventually approaches the equilibrium solution of 0. If you start even with just a few more than that, a few more than threshold, the population will grow, but it will still be capped in this case at the carrying capacity. And if you start with way too many, or even a few too many, then the population also approaches the equilibrium of capacity. So although these equations looked similar, they do look similar, they're very similar, they actually incorporate very different behavior into the solutions. And this one just adds an extra factor so that we can cap our population growth. I'm just giving you this in the same way that your textbook, frankly, gives you this equation. We're not going to derive it in the same way that we did this one up here. There are whole courses and whole careers made on how to model different situations, scientific, biological, physical situations. And that's not what we're in the business of doing in this course. It's important, I think, to see how formulas and equations come to be, but in this particular instance, that it's a bigger piece of the puzzle than we really need to involve ourselves with. So I'm just giving you this equation so that you are familiar with it and have seen it when you go to work through some of the problems that you'll be dealing with in the textbook. Something to keep in mind that we haven't really discussed is that, first of all, we haven't, with one exception on the previous screen, we haven't done any actual examples, right? We didn't take a differential equation with numbers in place of r and t and k. So we're dealing here with very sort of generic values, very generic graphs, and very generic concepts in a way. So I'm going to say now, because we've already spent so much time on this, that I'm not going to include an example in this video. If I have time, I'll create another video with another example. But the other thing I want to point out is that whether R and T or R and K, or all three of them are defined or not, none of these has any initial conditions associated with them. So if I take one of my equations and graph it in this way, I'm looking for what some potential solutions might look like, where I don't know T and I don't know K and I don't know R, I can only sort of guess at its general shape. If I know T, R, and K, then I can tell you exactly where this value is and exactly where this value is, and I might be able to be more accurate about my slope lines, but I still have a whole bunch of different situations going on. The only way I can determine if, I'm going to grab a highlighter here, see if this works. The only way I can determine what a particular solution is if I have initial conditions. Only then will I know that at time equals 0, for example, I had this many individuals in my population, and this is my specific solution. Or maybe I had this many individuals, and this is my specific situation. But those are different solutions, one from the other. And you can only find those solutions if you have initial conditions, such as y of 0 equals 100, right? The initial population, the population at time 0 was 100 individuals. If that's 100 right there, then that's that solution, okay? If y was equal to, well, y is never going to be negative, so although we can graph this, it's the same as any graphical application, right? We can graph this situation, but it's never going to exist in a population of individuals. We can never have a negative number of individuals. But let's say y of 0 was 10. If this is 10, then I'm looking at this situation. I'm approaching the equilibrium solution of 0. So keep that in mind as we go forward, that these are generic, many potential generic solutions to a generic situation, whereas having a set of initial conditions and values for R, T, and or K is going to change this into a very specific graph rather than one that just sort of shows you generally what the shape of the graph is.